In this tutorial, we will design a single-span precast girder bridge 110 feet long. The bridge has a total width of 55 feet 4.5 inches and consists of an 8-inch thick composite concrete deck supported by 6 72-inch deep AASHTO Type 6 precast girders that are pre-stressed. The bridge supports a total of 4 lanes of traffic, and the lanes will be loaded with HS-20 44 vehicles and lane loads. For this specific model, CSiBridge provides 4 different options for calculating the live load distribution factors. The live load distribution factors affect how the shear and moment are distributed to the girders. First is the option where the user can specify the factors, both shear and moment factors for interior and exterior girders, a total of 4 values. In this case, the model may either be a spine model, in which a single frame object represents the entire cross-section, or modeled with area objects. But in either case, there should be only a single lane that is loaded. The second option is that the program determines the distribution factors from the AASHTO LRFD code. Again, the model may use either spine or area objects, but should have only a single lane, which in this case is centered on the model. In the third option, the program determines the live load demands directly from the analysis, in which case the model must use area objects and all 4 lanes should be defined. In the last option, the program distributes the live load equally to all girders, and the model may use either spine or area objects, but all lanes should be defined. In this tutorial, we will use option 2, where the program determines the distribution factors from the code. Now let's get started. We will start on the Layout tab by defining a new layout line. The layout line defines the control geometry for the bridge. Our bridge will be straight with no change in grade, with a length of 110 feet or 1,320 inches. Next, we move on to defining the lanes. Remember, for our model, where the live load distribution factors are retrieved from the AASHTO code, we will define a single lane, which we will derive from the layout line. We will create a single 12-foot or 144-inch wide lane that runs along the layout line center line. Moving to the Components tab, we select the property type to be Materials. We will make some modifications. First, select the 4,000 psi concrete and rename the material Deck Concrete. The deck will be 4 KSI concrete. We will copy the deck concrete and create a material for the girders. we will adjust the modulus of elasticity, and the girders will have 6 KSI concrete. Lastly, click the dialog box launcher and then the Add New Material Quick button to add a material for the prestressed tendons. Next, we will define frame sections for the girders. We will add a new property, selecting Concrete and Precast I. From the drop-down list, select the AASHTO Type 6 beam. Note that all the dimensions are automatically populated, including the total depth D1. Switch the material to girder concrete. Now we move over to the Superstructure panel and select the Deck Sections item. Clicking the New button, we select the Precast I girder option. We verify the slab material, and we will have a total of 4 interior girders and a total width of 664.5 inches. The girders will be laid out along the layout line. The top slab thickness will be 8 inches, and there will be no haunch. The girder section will be precast girder, and the left and right overhang lengths will be 42.5 inches and the fillets 24. The distance to the edges of the curb will be 20.25 inches. Our finished section is as shown here. Next, we move on to the substructure panel and select the bearings. We will define 2 bearings, one at the left and one at the right. The left bearing will be fixed in the 3 translational directions. The right bearing will be changed to free in the layout line direction. Now we will define a foundation spring. The foundation springs will be fixed in all degrees of freedom. Next, we will add an abutment. The abutments will be connected at the girder bottoms and will be supported on foundation springs. the springs will be the previously defined foundation springs. But in this case, we could select fixed as well. We can skip the bents because our bridge spans from abutment to abutment. Moving on to the Loads tab, we will add the vehicles. First will be the HS2044 truck. Followed by the HS2044 lane load. Both the HS2044 vehicle and lane load will be combined in a single vehicle class. A check of our load patterns shows that only a dead load pattern has been defined. We will add a prestressed pattern for our tendon loading. We have no other loads, so we will move on to the Bridge tab. It is on the Bridge tab that we assemble all of the components for our bridge. Clicking on the New button, we create a new bridge object. The first step is to verify the reference line, which shows that we have a single span of 1,320 inches. We can make and verify our assignments right on this form, or we can use the buttons on the ribbon, which we will do here. Starting with the spans, note that our deck section has been assigned without variation. We can skip the span items, as none of these apply to our model. Moving on to supports, we select the abutments. With the Start Abutment tab selected, we will use the previously defined abutment property, with the substructure located at -120. And we will use the bearing left set at -96. The end abutment is almost identical. We will use the same substructure elevation, but this time we'll use bearing right at the elevation of -96. The only other bridge object that we need to concern ourselves with on this tab are the prestressed tendons. The tendon load should be applied using the prestressed load pattern. Verify that the tendon starts at the start of the span and ends at the end of the span. And input a total tendon area of 6.732 square inches. This is 44 tendons. Our tendon load will be 400 kips, and we will model the tendons as elements. We need to model the tendons as elements when doing a strength check. Click on the Quick Start under the vertical layout and select the straight tendon with bends 1 option. Click on the Edit Vertical Layout button and switch the vertical offset at the ends to -35 inches. We now wish to copy the tendon just defined into all of the girders. We can do this with a single click on the Copy to All Girders button. The Show All Tendons button displays the tendons in each of the girders. The last step on this tab is to make sure that the model is linked. If we had selected the Auto Update option, the model would have automatically been updated each time we made a revision. Instead, we will use the manual approach by selecting the Update button. Here we can specify whether the model is to be a spine model or to use area objects. For the live load distribution technique we are using, we can use either. For the area object option, the model looks like this. For the spine option, like this. We will use the spine option. Note that the pre-stressing is displayed. And we can show the single lane that we defined. Moving on to the Analysis tab, we can verify the load cases. We will delete the modal case but we'll add a case for the live loads. Select the load case type to be moving loads and make sure that the reduction factor is set to 1. Remember that in this analysis we are loading only a single lane. Now we are ready to run the analysis. Once the analysis is complete, we can switch our focus to bridge design. We start by going to the Design Rating tab, and under Superstructure Design, view the code preferences. Here, we can select the code, and we will use AASHTO LRFD 2007. Next, we move to the Load Combinations panel and click the Add Defaults button. Select the Bridge Design option and click the Set Load Combination Data button. This form lists all of the strength, service, extreme event, and fatigue limit states defined by the AASHTO LRFD 2007 code. To keep the number of design load combos to a relative minimum, in this example, we will pick only the strength 1. If we click on the limit state drop-down list, we see that this is the only limit state available. The load cases that will be used in the design combinations are shown. For the strength 1 limit state, the code specifies 2 design combinations. Click the OK button twice and return to the drop-down list. In addition to the combinations, the program also creates group combos. The Strength 1 group is simply an envelope of the associated design combinations. Note that this example contains few limit states. Most bridge models will contain substantially more of both states and combinations. Now that the design combinations have been set, we will set the design requests. Design requests are where we specify the type of checks we want to perform. For this model, we will do checks for the entire bridge, although the program allows you to specify checks for only a portion, if so desired. We will create a total of 2 design requests, one for shear and one for flexure. We will not do one for stress because we did not previously select a service limit state. We have only a strength limit state. Starting with shear, we will specify the demand set to use. Typically, one specifies only the group combination, as this envelopes all the design combinations that are part of the particular limit state. For this design request, we will select the Strength 1 group as the demand set combo. It is also on this form that we specify the live load distribution factors to use. We have set this model up to use the factors as specified by the design code, but with slight modifications such as updating the model with area objects and changing the lane loading, we could use any of the other 3. In fact, without any changes to the model, we could select the user-specified option where we would specify the 4 factors. But again, we are going to use the specified by code option with the default settings shown. It should be noted that the program automatically calculates the number of lanes based on the bridge width. Our second design request will be for flexure. And alternatively, we will specify both Strength 1 combinations, which will give the same results as if we selected the group combo. We will again ask the program to use the distribution forces from the code. Now that we have specified our 2 design requests, we are ready to run the design. Click the Run Super button. On the Perform Bridge Design form, note that we have the 2 design requests and the desired action. Click the Design Now button to start design. Design is computationally intensive and may take significant time. Upon completion of the design, the Bridge Object Response Display form is shown. Starting with Design Request Shear, the Strength 1 limit state generates a plot of shear demand versus capacity along the length of the bridge. Note that the demand is below 1, which is obvious with the DC limit checkbox checked. These shear values can be displayed for each girder, and we can also view the required shear rebar area. All the information displayed graphically in this form is also available in tabular format via the Show Table button. Select the shear property table, and the table displays the live load distribution factors used for shear and moment for the exterior and interior girders. Select Design Request Flexure, and we see a plot of moment along the entire bridge for the Strength 1 limit state. Click the positive resistance and negative resistance options, and we see that the moment lies within allowable values. This concludes this tutorial on precast girder design.